Okay, so now let's start working towards discussing rolling down an incline, and this is going to lead us to a handy review of energy also, but first the rolling part. So imagine one of these objects, it could be the disk, it could be the hoop, rolling down the incline. It has two pieces to its motion, right, because it's, let me put a word on there so we can see what it looks like as it's rolling. So as this thing rolls down the hill, the word up is rotating, the disk is not getting smaller. I'm just a bad artist. There are two components to the motion here. The complicated motion of the puck, and maybe it's not that complicated. So we can think of the velocity in two pieces. We've done this kind of breakdown before. Velocity of the center of mass plus the velocity relative to the center of mass. And in this case, the case where you're rolling without slipping, the relative velocity can be written as the radius of the object, so here I'm talking about the object, times the angular momentum, or angular velocity rather, of the object. So we can think of the motion as two pieces, center of mass plus rotation about the center. That matters because the way what I'm going to do here is relate the use energy conservation. We'll write down the energy of the disk at the top, we'll write down the energy at the bottom of the incline, we'll set the two equal, and we will solve for the speed of the puck down at the bottom. But the key part is that we're going to break this up into two pieces. And actually there's one other piece here. The other piece is that the angular velocity, so that's the, one way to think about that is that it's change in angle divided by change in time. And in everything we're doing here, we're really just talking about one component of the angular velocity out of the page. It's a detail you don't need to worry about too much, but to make sure that what I'm writing down here is accurate, I'll call this angular speed instead of angular velocity. Angular speed is change in angle or divided by change in time. So let's imagine we look at as our angle pi, so we do one revolution, and how do I figure out how fast or how much time one revolution takes? Well, let me draw out one revolution. So we start here at up, and then half a revolution later, the puck has rotated 180 degrees, and then another half a revolution. We're back to where we started. The distance at the center of the puck has moved here is the velocity of the center of mass, or the speed of the center of mass, I guess, times delta time. But that distance that we've moved, because we moved through one full revolution is also equal to 2 pi times the radius of the disk, and so this delta time is 2 pi r over VCM. And let's take that and put it back up into our angular velocity, or angular speed formula rather. So omega is 2 pi because we chose to look at one full revolution, divided by 2 pi r over VCM. I've flipped the fraction because we're dividing, and we get velocity of the center of mass divided by r. So there's a relationship between the velocity of the center of mass and omega, and that sets us up for talking about energy.